flow. So depending on the situation, you would use that. We didn't assign any of this problem, but these are mixed convection. Yes, there is. Now, with that said, this is all the correlation I want you to know. I suggest the correlation important for you to know. Number one, know the correlation of a vertical surface. Know the correlation for horizontal surface, top hot, bottom cold, know all of that. If you know vertical surface, you know vertical cylinder. Then for horizontal plate, you also could do horizontal cylinder. Horizontal cylinder is, and use that Churchill guy for both horizontal vertical plate or vertical cylinder and horizontal. There's Churchill, that complicated equation with many powers. Then remains a few small ones to know. So you have the. Now let's do this problem. I want to see again. This was the type of problem I assigned in one exam. Storm window. This is 7.56. So what is a storm window? Storm window. So suppose this is here outside. Outside is here. Then they usually have a gap here. This is the gap. And this is another window here. I have two vertical surfaces. Here a gap of air in the middle. Why air? This is inside. Okay, so essentially two vertical plate. This is gap in between. Air gap. Air is a good insulator. So you have an air insulator. I want to see how much heat is going through here. Storm window consists of two glass panes, 80 centimeter by 80 by 5 millimeter thick, separated by 10 centimeter of air gap. Heat loss through the window. Okay? How do you calculate heat loss? This is chapter 2 problems. The only thing you need H. So inside or outside, you have vertical. From external part of it is vertical plate. It's easy to calculate. Vertical plate, use Churchill equation. Inside the gap, use this gap equation. Use this guy. Inside the gap, use this equation. Okay. Sorry, I went through. Inside the gap, use this equation. Okay. So what I want to show you, let's see how we did it. So free convection, vertical plate. First, the only thing missing here, they don't have the wall temperature. They have inner temperature 0, outer temperature is a cold day. Outside is 0, inside is 65 room temperature. They don't have the wall temperature. Now, as you know, you need for natural convection delta T. What is that? T wall minus T infinity. I don't have T wall. Couple of our problems, if you don't have T wall, just guess it. Guess it, and because I have 0 and 65, I just guessed it about 55 here. The wall temperature. Now you could repeat this. It's just trial and error procedure, but I accept that. You need to look up your properties. Properties doesn't change that much with temperature. So assume T wall 55. So 55 plus 65 divided is 60 real temperature. Then go ahead, go to the properties table. K of the air 0.028. K is very small for air. G beta nu for air 8.7. Then length you have. Then calculate Grashof number. Go back to figure equation 735, that big equation. Remember Nusselt to the 1/2? Or figure 7.6. Calculate HI. So you calculate Nusselt, then HI. So this is vertical plate inside. So you're talking about this side of the problem. A vertical plate, right? A vertical plate. This is inside. Now do the same thing for outside. Again, 15 plus 0. Assume the temperature is 15 outer plus 0, the outer wall. 0 is the outside is 7.5. Conductivity, G beta nu, L Grashof number. Again, use the same equation, 735. Now, what about air gap? Air gap, I have the two wall temperatures. Look at the properties. Now you calculate the aspect ratio, calculate C, calculate Nusselt number for the gap. So I calculated H of the gap. So how do I use H of the gap? This is the trick. Now I have this wall, I have this wall, and this is the gap. So I want a resistance here, a resistance here, a resistance here, a resistance here. Now forget about the resistance of the wall. I have 1 over HI, 1 over HO, A, right? What about this here? Usually if it's just solid, it's L over KA. So L over K area is the same. It's the same as convection of the gap. When the resistance, you see this is resistance. But I calculated H of the gap. So I set this to equal, so I calculate for K effective. This is not in the solution. K effective becomes L times H of the gap. I multiply and divide by K, so I get K effective equal to Nusselt number times K. So K effective here is Nusselt number multiplied by K. So I get the K effective, so I put my chapter 1 problem, 1 over HO, 1 over HI, delta XJ, L over K effective. Calculate sum of the R's, and Q equal to delta T over R. All right, this is chapter 6 problem. Everything in chapter 6. Now, any questions before I want to, we are right now 7:12. I just want to go back to, if you have any question, please raise it before I go to another window. While I'm in here, please raise your question. Okay? Anybody has question on natural convection? That's all natural convection. I summarize everything for you again. The most important thing in natural convection is knowing that Nusselt number is function of Grashof and Prandtl number. Step number 1 is this guy. That's the all correlation, or is product of is Rayleigh's. Okay, that's the whole thing. A little bit know how the temperature, velocity, density changes. Forget about derivation. The first equation you want to know, there are a lot of correlation for laminar and turbulent flow in the book. I would stick to general correlation for vertical plate, is this one. This correlation, Churchill, and the corresponding graph. You could also use it for vertical cylinder. Okay? Then horizontal plate. Upper surface hot, lower surface hot, upper surface cold, lower surface. So they divide the two cases. Upper surface hot, lower surface cold, upper surface cold, lower surface hot. These two cases, this equation. Then horizontal cylinder. They have like Churchill equation. Did a lot of problems. Then I went to did the steel problems. I went to this air gap. And that aspect ratio was a parameter. Either aspect ratio between 2 to 10 or 1 to 2. Have two correlations. Or use this figure 7.9. You see, with internet, now I have everything right in front of me, and I could review it for you so that you see what we have done all together. And then you're not responsible for combined free and forced convection. Let's go over this problem. Anybody has any questions?
All right, now.
Okay, let's go to record. Okay, let's go back to participant. Okay, we have everybody here. Let's see. Anybody has question, dear friend? Let me know. Trevor Cole, are you there? Hello, Trevor. Do you hear me, Trevor? I hoped you could hear me. Matthew, do you hear me? Hello, Matthew.
Yeah, I can hear you.
Okay, do you have any question?
No.
You mean you followed everything so far?
For the most part, yeah.
No question. Have you done any of the problems so far?
No. I've just been looking through them and stuff, but
Okay.
yeah.
Okay, let's see. What about Dennis? Dennis, do you have any problem? Pause.
I'm not. I'm sure I'll have problems after I do the homework, but I haven't looked at that yet.
Okay, but this is not a big deal at this stage. I want to.
No, this chapter looks a lot easier than chapter 6, to be
Oh,
honest. So I don't think that.
I mean, it's just 5 or 6 correlation: vertical plate, vertical horizontal plate, vertical cylinder, horizontal cylinder, and then a gap, a few natural convective flow, and that's Q equal to calculate H for natural convection. The only thing you have to know is Nusselt is function of Grashof and Prandtl, or Rayleigh's number, nothing more. Now, radiation is a little bit more. Now, in this, let me go back to, maybe let's go back to problems. I want to go to problems. Somebody had this first problem, who was the person who asked the first problem? Chapter 7, let's see, where is that problem? I also gave homework chapter 7. Okay, chapter 7. Okay, this chapter 7, you see at the beginning of the homework, you have all this table of chapter 6 that summarizes. Then this is the homework of chapter 7. Now, the beginning one is just gives you a little bit practice of vertical plate. Calculate Grashof number. Okay? Just for air, water, mercury. Let's do some of this so that you are easy to. The only thing you need to do, find the T average and calculate this Grashof number. G beta nu delta TLQ. Okay? And for different properties, just look it up and calculate Grashof number. Now, as you see, Grashof number for all these cases are turbulent flow. You're not responsible for 7.6. 7.6, if you are doing analytical, do you remember the equation I gave you? You simplified it. Momentum and energy equation. If I wanted to ask you to do analytical, you simplify these two equations. And the left side becomes 0, the original equation I gave you in the note. So you solve for temperature and velocity field. If you have the velocity and temperature field, you could calculate Nusselt number. So you're not responsible for that. 724 is what it said. Is it 724? Yeah, we did 724. I did that 724 for you. This is the one that has calculation of Biot number, and it's a conduction plus convection problem. Vertical plate hanging. I did this in class. 744. I did that. A hockey rink. I did that. 746. sphere, I did that. 746, I did that. 756, this is the gap problem. I did that. The gap problem, I did. Somebody was asking me, somehow I didn't, there's another problem. You're not responsible for that. It's trial and error. Is 7 point, anybody did 7.22? Did I say do 7.22?
You did.
Okay, forget about 7. 7.22 is, and I don't have the solution here for it, so don't forget about that. It's if you want to do it, go ahead, do it. When you don't have the temperature, the wall temperature, right? The wall temperature is not known. So how do you calculate Grashof number if you don't have the wall temperature? So you have to guess the wall temperature, okay? Guess the wall temperature, guess the film temperature. Now, then solve for, and you go to calculate that, you write Q, you were given Q, so Q equal to H, A delta T, you could solve for H. Okay? So you get an equation for delta T, so based on that, you guess delta T, you calculate it, so it's a trial and error procedure. Forget about it. That problem, omit that problem from the solution. This is a trial and error procedure, omit that problem. You want to include it, it's going to take you a long time. I don't know why I included that problem. With that said, if you have any questions, otherwise I want to give you a break and go to chapter 722. Go to chapter 8. Okay? Let's see whether I have it here. Let's get rid of this. Let's get rid of this. Everybody, if you want to get ready for chapter 8, leave. Okay. So I want everybody go to, you have this, go to chapter 8. Everybody go to chapter 8. So we try to see as much cover as we could. Now, of course, I also have Tuesday, but I want to go at least over the whole chapter. And Tuesday, I spend the time going over it again. As you see, each chapter, I cover it essentially twice. I go over it again. Now, the problems, you might ask me, when are those due? Now, I make this last week a little bit, I let you work, get ready for the exam. That's why I didn't give you another exam. To tell you that I wanted to give you an exam today. Let them work on this chapter because there is a lot for them to accomplish. Exam, as I told you, is 40%. So it covers, let me just briefly tell you what it covers so that you know exactly what we are talking about. If you look at towards the end of this section, okay, I'll go over this, but if you look at towards the end of this, I'll go over all of this. I made this so that you have it before the weekend. This chapter 8 is new, but it's not that bad. There are two, I tell you what problems you are responsible. It's a little bit more complicated than the previous chapter. Electrical analogy is important, and I wrote a section about what are your response? Okay, final exam. You want to see that? It's written on the last page of this final exam. One problem, chapter 8. And I'll tell you what it is. Between today and next week, I tell you exactly, and you would love it. Chapter 8, the radiation. Radiation, you will see, it requires a little bit to get used to it, but then it's not that bad. It's better than chapter 4. Chapter 4, you saw I gave you a problem, you got stuck. So chapter 8 is much better. Chapter 2. Problem 2, Chapter 7, natural convection. Problem 3, force convection. Problem 4, Chapter 2, 3, 4, conduction. The 2, 3. Problem 5, combined conduction. So I'm not going to give you 5 problems. Maximum of 4 problems. Maximum of 4 problems. Any questions that you have in regard to exam?
Yes. Would it be possible if we push the exam like to an earlier time instead of the 6 o'clock class time?
Okay, that would be a good suggestion.
Right.
Means
6 o'clock
give
is
the,
a bit late.
give the exam earlier.
Yeah, maybe like 2 o'clock in the afternoon or something like that.
Okay. Yeah. 2 o'clock in the afternoon on.
If that's cool with all the other students too,
Yeah. What about everybody else? Could you tell me, everybody else, give me some feedback right now? What you think? Some people are working or some others. What do you think? I want everybody to be there. Could you give me feedback? I don't want to go through the names. Could you give me everybody feedback if you agree with this proposition?
Yeah, I think it'd be better if the exam was earlier also.
Okay. So
How long is the final exam?
3 hours.
Okay.
Professor Hong is there. What about Curtis? What do you think?
Oh, yeah, 2 sounds good.
Alex, did you say it's okay? Hello, Alex Worrell.
Yeah,
Well-
I said it would be better.
Chris has said okay. Then Curtis, did you say okay?
Yeah.
Dennis, okay?
Yeah, I was the one who suggested it, but yeah, that would be great.
Okay. Lucas,
Yeah, that works for me.
Matthew,
Yeah, that sounds better.
Iker,
Yeah, that's fine.
Stephen,
Yeah, sure.
Trevor, Cole. Hello, Trevor.
He typed something in the chat. I think he said it works for him.
Oh, I see. Some people maybe sometimes they, I have problem with my microphone. Some people cannot hear or something wrong. Okay. So what I'll do, I let you know. We still have time because on Tuesday we meet, right? So we meet on Tuesday. We'll go over that and then. But the suggestion, everybody want to take the exam around what time do you want to take it? Everybody just be about 2 o'clock. Is it good? Or earlier?
2 o'clock works.
2 o'clock.
Okay, 2 o'clock.
That's good.
All right. All right, with that, take a short break and we'll go over radiation. We'll go briefly over, and I tell you exactly what is, what do we have to do? It's all right. I'll see what do we have to do. Let's go over that.